And all of you can come tomorrow to the event if you want. It will start at next day then.
Okay, so let us start. I don't think anyone else is coming. So, am I audible to everyone? Okay, fine. Good evening, everyone. This is Abhimanyu. I am a second year PhD scholar at IIT Delhi, and this is the fourth week of the interactive session of the course MATLAB programming for numerical computation. So, initially, we will be going through some of the, we will be doing a recap of what was taught in the lecture videos of the week 4, and then we will solve some problems. We will code them. And then I will try to solve, if we have time remaining, then I will try to solve the sample problems that is there on the NPTEL site. Fine. Uh, so let us start with rank and solution. Yeah. So this is a matrix, so n by n matrix. So, we have m number of rows and n number of columns. So if m is not equal to n, then that's a rectangular matrix, and if m is equal to n, then it's a square matrix. Uh, we have seen in those lectures that for a square matrix, we can simply try to solve the problem, a linear problem, as we can try to find x using A inverse B. Now we already know this from our 12th, 11th, 12th, and BTech first year, that to find the solution of this system, the solution only exists if the determinant of matrix A is non-zero. If the determinant is zero, then the solution does not exist. So this determinant is equal to A is a necessary and sufficient condition for a solution to exist. Now, if the solution is unique, or do we have a non-unique solution, that depends on the rank of the matrix A and the augmented matrix AB. We will see that next. Yeah. So we will look at this example, and we will try to see. So we have three conditions. One is if the determinant is equal to zero, then the solution is not possible. Then the other thing is that if rank of matrix A is same as rank of the augmented matrix, then we have a unique solution. Otherwise, if this rank is same, but it is less than the number of unknowns in the system, so n is the number of unknowns in this case, that will be like, if we look at this example, then those will be two unknowns. So if the rank of matrix A is and the rank of augmented matrix is same, but it's less than 2, then the solution exists, but the solution is not unique. The second case is if the rank of matrix A is less than the rank of matrix B, less than the rank of the augmented matrix, then the solution does not exist. So we will try to see these examples in MATLAB. I will just keep it over here for academic use. So we will look at these examples later. First, let us create these matrices. So we have A and B matrices. Now let us first try to find the determinant of this matrix. So we will just type determinant A, and we see it's a non-zero determinant, so the solution exists for this system. Now, right now we are trying to solve the first problem where the B matrix is 3 comma 3. So I will create an augmented matrix. So this is the augmented matrix. We will try to find the rank of the matrix. So rank of matrix A, the rank of the matrix A is 2. Similarly, if we try to find rank of the matrix, augmented matrix, so both of these rank are 2, and we have two number of unknowns. So that means there is a unique solution to this problem, and we can try to find that unique solution using backslash operator. So just write x backslash b. This gives us the answer 1 comma 1, which can also be easily seen using this. 1 comma 1, so 2 plus 2 times 2 plus 1 is equal to 3, and similarly 1 plus 2 is equal to 3. Now if I change the B matrix, so I keep the A. Now if I change the A matrix also, so we will do these two examples. So if I change A matrix to 2 comma 1 and 4 comma 2, right? Let me yeah. So this is my A matrix, and similarly my B matrix would be 6 comma 12. Fine. So first we will check the determinant of A. So the determinant of A is 0. Okay. So there is no unique solution exists for this problem, and uh, there are a number of different solutions, like infinitely many solutions are possible for this. Like we need to now, since we have checked the determinant of A and it's 0, that means no unique solution exists or no solution exists. And now we need to check the rank of the matrix and the augmented matrix. So let us first check the rank of A. So the rank of A is 1. Now if we check the rank of augmented matrix, so both of these rank is 1. Okay, that means if I go to condition, it's here only. So you can see that this A and B matrix, this satisfy the first condition. So rank of A is equal to rank of the augmented matrix, but the rank is less than n, which in this case n is equal to 2. So the rank of the augmented matrix is less than 2. That means we have infinitely many solutions possible. Okay. Also, you can see that these two equations are basically same. So if I divide row 2 with the 2, like entire augmented matrix with 2, then I get basically the first row only, 216. And if I divide this by 2, then 216. So it's basically these two equations are same equations. So uh, these are like lines which are superimposing on one another. Two lines superimposing on one another. So we have infinitely many possible solutions. Furthermore, if I keep my A same and I change my B, so I change my B to 6 comma 9, 6 comma 9. Now if I try to find rank of A matrix, still it's 1. But if I try to find rank of B matrix, augmented matrix, so I get rank 2. That means there is no solution exists for this problem, because the rank of augmented matrix is not same as the rank of matrix A. Fine. Any doubt in this? Okay. So we have seen the existence and uniqueness of solutions. Now let us look at dense and sparse matrices. So suppose I write the number of entries in a matrix as number of non-zero entries in a matrix as nj. So here, like, I am talking only about square matrices. So if the total dimension of a matrix would be n square. So the total dimension of my matrix is n square. Now, the total number of non-zero entries, if it's very less than the total number of entries in the matrix, then that matrix is called a sparse matrix. So suppose if I have, suppose I have a matrix where I have only have diagonal entries, and like I have a tri-diagonal matrix. Okay, so I have these three diagonal elements, and rest of all the elements are zero. So this is called a sparse matrix. MATLAB has a command also known as sparse, where we can store these. So we only need to store the elements which are non-zero and the index of those elements in MATLAB. How or why this helps is that suppose I have a n cross n matrix. So I have total n square elements, and each element is a 8-bit integer. So I need 8-bit into any square number of a number of bits in the memory to store that matrix. But if I have a sparse matrix and I only need to enter the non-zero elements, then I need 8-bit for the value of that integer, and 8-bit for the address. So I only need like 8 into 2 times the total number of non-zero elements, which is nz. So I need 16 times nz number of bits, which is very less than 8 n square number of bits. So that is why they are advantages, because they require very low memory and can. Next, we have diagonally dominant matrix. So a diagonally dominant matrix is something which has the diagonal element is the absolute value of diagonal element is greater than the sum of all the other elements in that column, in that row. Okay. So you see here is uh, this is a not a strict inequality. So, and if we have a strict inequality, then that is called a strictly diagonally dominant matrix, or a strongly diagonally dominant matrix. Right? We will look at some examples. So first, let us know why these matrices are important. So diagonally dominant matrices are important because the diagonal element, because they can be inverted with very little number of arithmetic operations. Like in most of the iterative schemes, either it's Gauss elimination or Gauss-Seidel elimination or Jacobi iterations, all those schemes work very nicely with diagonally dominant matrices, because we need less number of computations to invert those matrices. All the major elements are across the diagonal, so if the operations that we do, the row operations that we do, it does not make the uh, elements that we get after the row operations very small or very large, right? So that leads to a numerically stable solution. That is why diagonally dominant matrices are important. So the first example is this matrix. We can see the sum of like if we see the first row, then we have all the zeros and we have only one. So the first row is diagonally dominant. Now if we look at the second row, then the absolute value, so it's equal to, like, a22 is equal to a12, a12 and a22 is equal to sum of a21 and a23. So this is not a strict inequality, but still the equality holds. Now, if we go to row 3, then it's still strictly strict inequality. So in total, this matrix is diagonally dominant, but not strictly diagonally dominant or strongly diagonally dominant, because second row does not satisfy the criteria. If you look at this matrix, so the first row, it's not diagonally dominant. The second row is also not diagonally dominant. Some of these two elements would be 4, but the middle one is only 2. The last row is diagonally dominant, but overall, since the first two rows are not diagonally dominant, so this matrix is not diagonally dominant. Now, if we look at this one, so in this, like if we look at the first matrix, so in this matrix we have two rows which are diagonally dominant. But if we look at this matrix, so this row is diagonally dominant. This row, there is a equality. There is no strict inequality, right? And also similarly for this, there is a not strict inequality. There is equality. So even though this matrix is diagonally dominant, we have only one row which is diagonally dominant. So the diagonal dominance is less than what is present with the first matrix. Now, if we look at the last matrix, so this is similar to this, same as this matrix. Uh, we have the second row swapped to the first row. So we have 1 minus 2 1 1 0 0 0 minus 1 0 1. Now if we swap these two rows, like the what, so we will get this matrix. But this matrix, we know that it's diagonally dominant. But if we look at this matrix, so the first row is not diagonally dominant. The second row is also not diagonally dominant. So this is not diagonally dominant. This is not diagonally dominant. This row, there is a equality. There is no strict inequality, right? So this matrix is not diagonally dominant. But if we pivot the first and the second row, interchange these two rows, then we get this matrix, which is diagonally dominant. So this is called pivoting, which you have also learned in the lectures, right? And we will also see one example of this as we move forward. Any doubt on in this, anyone? Uh, Fine then. So let us look at Gauss elimination, right? So this is the uh, code, not the code. This is the flow chart or pseudo code for Gauss elimination. So we have A and B matrices, which we get from our problem statement. We create an augmented matrix AB. Then for each step, we get the yeah. Then each step, we take the diagonal element as the pivot element, and we do these row operations for each row. And then once we get a upper triangular matrix, so a matrix which is similar to this structure. So these are all the non-zero elements, and these are all the zero elements. So once we get a upper triangular matrix, then we do back substitution to get the values of x, or the unknowns, right? Let us try to solve this problem. This problem is similar to what we saw in the recorded lectures, same as the one we saw in the recorded lectures. For we go to MATLAB. And so and this is the matrix. Uh, So we have a matrix 1 1 1. So the first the coefficient of the first equation 1 1 1, and for the second 2 1 3, 3 4 minus 2, and we have the constants 4 7 and 9. So we have these two matrices. Now we need to create a upper triangular matrix for this Gauss elimination. So first we will create an augmented matrix AB, and then we'll just calculate the size of the augmented matrix. So this will give us the number of rows present in the augmented matrix. If I run these two commands, so this is my augmented matrix, and n is equal to 3. So I have 3 number of rows. Now this is like I've written a journal purpose code, so you just need to enter any A and B matrix and this code will run. But first we will try to see it single row wise. Okay, so let us try to see for the first row first, not the first row, second row. So for a diagonally, so for upper triangular matrix, the first row will remain the same. Whatever matrix you have, the first row will remain the same because that is the diagonal element, and the rest of the elements you don't need to change. All the operations will be starting from the second row, right? So for the second row, our pivot element would be A11, like AII, that is A11. So my alpha would be A11. Then I will do the operation on the second row. So I will change the augmented matrix. Second row, I will replace it, like I will multiply it by alpha times the first row, right? So if I run this command, if I see my augmented matrix, if I 1 comma 1, yeah, sorry, I took the wrong alpha. So my alpha should be A2 comma 1 divided by A1 comma 1, right? Oh, sorry, so I just need to run this one again, because that will, otherwise my A augmented matrix would have changed. Yeah. So now my for my first element of second row has become 0. Uh, now I need to make the first element of the third row 0. Okay. So similarly, I will do for the third row. So my alpha would be 3 comma 1 divided by A 1 comma 1, and I will change the third. Fine. So now if I run this, I will check my augmented matrix again. Yeah. So now the third row first element has become 0. So we have made the first column. We have made the first column 1 0 0. Now we need to move to the second column. And for the second column, the first element, the first row need not to be changed. So we will. So now for our pivot element would become. So this is for the second row. First like if I run it in a loop, then this would be my first loop. Then my second loop would be, my alpha would be, I need to take this element, so that would be 3 comma 2, divided by a 2 comma 2, right? So I will be dividing this element by this element, and then I will be changing my third row. So I will multiply it by the second row, because we have taken our pivot element is the second element. Okay. So if I run this, uh, some error happened. A3 comma 1, so 3 comma 2 would be there, and A2 comma 2. This one, this was a pivot matrix. So my alpha would be -1, minus minus plus. A1, 3. This should have worked. So let us run this part again. So this is our augmented matrix. Now we need to take we need to take this element A32. We need to divide it by A22 minus 1. So we will get alpha. So if I run this line, so my alpha would be 4. Why is my alpha 4? Sorry. Yeah, so what I was doing wrong is I need to take the augmented matrix elements over here. Because when we are doing these row operations, our a matrix is changing. So if I look at my current augmented matrix, and if I look at my current a matrix, so this matrix, this second row is different from this row, right? So I will just take my augmented matrix over here. See, my a3 comma 2 is different. My a3 comma 2 is initially 4, and my a22 is 1. But what I need to do is I need to have this as a3 comma 2. Like I need to have 1, right? Right now, what is happening? I am dividing 4 by 1, so it's giving me 4. That is why the error is happening. So I will take this augmented matrix values, and I will do this. Then it should work now. So first I will do this first part. This is my augmented matrix. Now I will do the second part. Yeah. So now this has become clear, right? So I have so now my A matrix is this 1 1 1. So if I so this is my A matrix, and by B matrices I will store, and by B matrices uh, 4 minus 1 minus 4. Okay. Now I just need to do back substitution. We have this augmented matrix, and now my x3 would be, we will be doing back substitution from the bottom row, and so my x3 would be minus 4 divided by minus 4, like a33 uh, b33 divided b3 comma 1 divided by a33. And once I get my a33, once I get my x3, I will just put it in my second equation. And I will calculate my x2 and I will calculate my x2. And similarly, once I get my x2 x3, I will put it in my first equation and calculate my x1. Okay, so my x1 would sorry, I will be starting with my x3. My x3 would be augmented 2 comma 4 divided by, let us just calculate, get the a and b matrices. Okay. And now the matrix will be fine. And now x3 would be a3 comma 3, sorry, b3 comma 1 divided by a3 comma 3, right? Because rest of my elements are 0 for this A matrix. So these two elements are 0. If I multiply this, if I write it like ax is equal to b, then if I multiply this row, then I would only get minus 4x3 is equal to minus 4. Rest of the other two elements would be 0. So that is why we can just directly write it. We can directly back substitute this like this. Now let us calculate x2. So if I write this, then that would be b2 comma 1 minus, I need to subtract 2 comma 3 multiplied by x3 and divide this by a2 comma 2. So this will give me x2. Right? This will be my v21. I will multiply this by a23. This is my a23. I will multiply it by my recently I got it x3. So I will multiply it by x3. I will subtract it and then I will divide it by a22. That will give me x2. Now for x1, I just need to repeat the above process. So 1 comma 1 minus a 1 comma 3 multiplied by x3 minus a 2 comma 3 multiplied by x2 and divided by a 1 comma. Fine. So if I run this, then my x1 is 1 to 1. Okay. Now first let me take the initial matrices. If I calculate determinant of A, then it's 4. So there is a unique solution exists, right? Now I calculate rank of A, that is 3, and rank of augmented matrix, that is also 3. So we have a unique solution. Now this is what we got using Gauss elimination, right? Uh, so this is what we got using Gauss elimination. Now if I do the backslash operator, y, So I'm getting the same answers 1, 2, 1. Okay. And I can also use the finally the matrices, the upper triangular matrix that I got. I can also use them and do the backslash operator. I will get the same result. So now this is my upper triangular matrix and this is my B matrix. If I do backslash operator on this matrices, then also I will get the same answers 1 to 1. Okay. Uh, so this was for the basic hard coding part, right? Now if I try to do it in a loop, this is hard coded part. If I try to do a loop implementation, then I will start my loop. I will start my loop like n is my total number of unknowns. That is my n. So I will run my loop three number of time. Like for this, in this case, I have three unknowns. So I will run this loop for two number of times. Similarly, I will start this. I will run this loop with whatever value of I is, and from that value of I plus one, I will go to n. So basically, for the second row, I will be running this loop two number of times because like my I would be one, then I plus one would be two, and my n is three. So this loop will run from two to three, two number of times. I am doing the same thing. So I am taking the okay, let me use breakpoint method to do this. That way we can see what is happening. First I will run this part. Okay, let me clear the workspace. So I got my AB and augmented matrix. Next I will run this part. Yeah. So right now my I is 1, my N is 3. Go to next step. My J is 2. So J begins from I plus 1. So my J is 2. Now I calculate my alpha. So alpha is 2. This is same as what alpha I was getting over here. So J comma, so right now. Yeah. So J is 2, I is 1. So I am basically doing augmented 2 comma 1 divided by augmented 1 comma 1. So my I is 1. So this is basically augmented 2 comma 1 divided by augmented 1 comma 1. This will be my alpha, first one. Then I have just replaced this equation with this parameterized equation. So my J is 2, my J and my I is 1. So I am basically writing augmented 2 is equal to augmented 2 minus alpha times augmented 1, right? So if I run this, what has happened? Okay, just a minute. I clear the workspace and I run this section. Then I don't run this section, I directly go to this section. My augmented is this right now. If I run this section, yeah. So after two iterations, my first row became my first column, it became 0 after the first element of the first row, right? Next, I will run this again. So now my I has become 2. I am doing the second loop, this part, and my J would only be this inner loop will only run once because my I plus 1 would be 3 and N is also 3. So my j is become 3, and now I will just do this part. Okay. So now my augmented matrix, so my A matrix has become this upper diagonal matrix. Hope you can see this. Fine. So now I will exit this loop, and now we will go to back substitution. So I'm initializing my x unknowns to a 0 vector 3 comma 1, and this is the last element. So x3 is equal to last element of the augmented matrix divided by this element of augmented matrix. So my x is okay. So my x is 0, 0, 1 as of now. Now I will just run this part. Okay. So what I'm doing right now is I am running this loop from n is equal to n is equal to 3, so n minus 1 from 2 to 1. So it will run two number of times for x2 and x1, and I am doing augmented. This is the this is the yeah. So this will give me the last. This will give me this element. Okay. So like my I would be 2, and n means I am getting this element, second element, last element of second row. Then I am multiplying I to I plus 1 to n. So this is a 3 cross. So this is like my I is 2 and 2 to 3. So I'm getting this part. Okay. And I'm multiplying it by x up to from the second element to the last element. So I'm if I take this, so this part would be uh, 0 comma 1. Okay. So if I take I as 2, and I will just run this. So right now my I is 2. Okay. And n is 3. So I'm getting this part. Okay. And if I run this, I'm getting the last element 1 x3. Okay. And I'm just dividing it by this minus 1. Okay. Sorry, augment. Yeah, so I'm dividing it by minus 1. So this will give me x2. Okay. So if I run this, yeah, so now my x would be minus 1 and 2. Now for the last part, so my I is has become 1 now. So it's running a inverse loop, like from 3 to 1. Okay. From 2 to 1. Now if I do this whole thing again, so now this will be a 2 cross 1 vector minus 1 1. This would be a 2 cross 1 column vector. So I am doing a dot product similar to a dot product. So my 1 1 multiplied by 2 comma 1. So this will give me a constant scalar value, and this would be the last part of augmented matrix. This minus 4. So minus 4. So this whole line is basically this part. Okay. And now I'm just dividing it by the first element. So I will be getting my last element of x. And then I will be displaying the results. Minus 1, 2, 1. Okay. So yeah, so this is the loop implementation. This is the hard-coded part. These are our problem definitions. Any doubt, anyone? Fine, then I will go to the next part. Just keep this over here. Yeah, so in the tutorials we have seen okay, we also saw LU decomposition, right? So let me do that also. I think I have not mentioned this in the presentation. Yeah. first, I think MATLAB has an inbuilt LU decomposition code. Yeah. So if I will give a matrix to this LU function, it will give me the lower triangular matrix and upper triangular matrix corresponding to that matrix A. So for our case, let us take this. Let me clear this. So this is my A matrix. Now let us do the LU decomposition on this only using the inbuilt command. So this is my upper triangular matrix. This is my lower diagonal matrix. Okay. If I do the Gauss, like the matrix that we are getting using Gauss elimination, run this part. So you can see this matrix is not same as this because it is doing some normalization inside the code. So we are not getting similar matrices, but the basic principle is same. I can get what I can do is yeah. So what we can see is that this LU decomposition, it's not unique. We can get different LU decompositions for different matrices. Fine. Uh, there should be some method from which we can go from here to here. Like if I divide the last row with, there should be some more functions inside this. Yes. So the LU decomposition that we get using the inbuilt command is different than what we are getting using the Gauss elimination. But basically what is happening is that we have a we have a where do I write? Let me just write over here only. Right. So for our case, this would be one, this would be one, this would be one, and these values would be alpha one. Yeah. This would be my alpha one. This would be my alpha two, and this would be my alpha three. Right. And all of these elements would be zero. The upper triangular matrix that we are getting from LU decomposition function is different than what we are getting, what we will be getting using Gauss elimination. Uh, yeah. So now this alpha one is basically this alpha, right? So whatever alpha we are using over here, this is same as the alpha one, alpha two, and alpha three. So if I name this as alpha one, alpha two, and this would be my alpha three. and I initialize my diagonal matrix. This will give me a diagonal matrix. Use I. It's not a problem. This will give us a diagonal matrix, and now we just need to replace these elements, right? So my L2, 1 would be my alpha 1. Similarly here my L3, 1 would be alpha 2, and here 3, 2 would be alpha 3, right? So now if I run this part, okay, let me run this, then I will run this. So I am getting my L matrix as this, and my upper matrix is similar to what I will make this as U, because this is my upper triangular matrix now. Fine. So this is my L, this is my something. This section. Oh, sorry. Now this is my upper L matrix, and this is my U matrix. If I multiply these two, I get back my original A matrix 1 1 1 2 1 3 3 minus 4 2, which I can see this. Yeah, so I am getting a 0 matrix. Now if I use the inbuilt command, this is also correct. If I multiply, so I'm still getting a 0. For our practical reasons, this is close to 0, 10 to the power minus 15. But this decomposition is not same as what we are getting using Gauss elimination. So this inside the code might be MATLAB might be using some different algorithm to calculate this LU decomposition, which is not similar to what we are doing, which is Gauss elimination. Okay, but still this is still a valid representation of A and B of A matrix, right? So why do we need to do this LU decomposition? Why we do this? So in this case, we are practically doing it because we can write this whole problem as equal to B. So this is our problem, right? Now if I change if I change this A matrix to LU, right? And now I combine this U and X together. That becomes Ly is equal to B. If I see over here, then my L is already a triangular, a lower triangular matrix. I can do back substitution, beginning with x1 and then go to x2 and then go to x3, and I can get my y vector easily. I don't need to do any Gauss elimination first to create up a triangular matrix. Then once I get my y, then my once I get my y, then my ux is once I get my y, then my u times x is equal to y, and my u is again upper triangular matrix, right? So if I try to do this, then my L is this. Uh, First, I will calculate, yeah, and my B remains the same. So first, I will just do my Y. I'll calculate my Y. That would be L backslash B. So this would be my Y, this Y, and now I will again do the backslash operation to get my X. So my X would be U backslash. So I'm typing. Why is it different? So I'm getting correct over here. Then L times U minus A. This is also fine. So I will just do my y as L into the inverse function times B. Okay, so this is correct. Let's replace this with Z. Then my U times uh, Z transpose minus Y should be 0. This is not coming out to be 0. Why is that happening? X is equal to B. We replace X with LU. LUX is equal to B. And then UX is equal to Y. B remains the same. We take inverse of L times B to get Ux is equal to Y. This should work. Why is this giving me error? U decomposition is correct. Does anybody know what is the error? I'll do it over here. I'm getting a different text. I don't know why. This is correct. Yeah, okay. Sorry. So I'm using this different P matrix. That is why the error is happening. Let me use the original V matrix. Yes. So now my X is same 1 to 1, right? So yeah, I was using the matrix that I got after the Gauss elimination to calculate this LU to get this to solve this LU decomposition. That is why I'm always getting different answer. So you need to use the original matrix. Okay, fine. So does anyone has any doubt in this? The Gauss elimination and LU decomposition? Okay. Now let us look at the pivoting part. So for the same problem, we will be doing a pivoting operation where we will be pivoting the second row to we will taking the third row to the second we will taking the second row to the first row and the third row to the second one, first row to the last one. Okay. If I run this whole command, first let me clear. Right. So if I run this whole command now, first I will run this section. So this is the matrix before the pivoting. Just this loop here only. Start new loop. So this is our matrix after pivoting. What has happened is if we look at the first row, right, then first column, then this is our pivot element, and all the elements below the pivot element is smaller than pivot element. What this helps us to gain is that we are dividing a smaller element by a larger element, so we are getting a number that is less than 1. So our overall our problem would if this is not, if this would have been not the case, then we might have some bigger number over here, some very large number, right? And if we will be dividing it by a smaller number, then we will be getting a very large number. So our alpha would become very large, right? Then this was basically give us take us to a value that is like minus infinity, right? That is why we need to do pivoting to make sure that that the alpha values that we are getting is less than 1, or some number that is uh, closer to small, not a very large number. Okay, so this is what we are getting after pivoting, and rest of the operations now we can similarly do the Gauss elimination like before. So what is happening in this pivoting section is let me do this using the hard coding way. So first we will take the first row, right? First column, sorry. So of the augmented matrix, we'll calculate the max of this. So val and index max call one, call one. Okay. Now if I run this part, I only run this section. So my value is 3 and my index is 3, right? This is my augmented matrix. In the first column, this is the biggest element, and it's at the third position, right? So now what I need to do, I need to take this entire row and replace it with the first row. Okay, so I will just store this in the temporary variable. So entire row, and I will make the first row of augmented matrix as 10, and then I will replace the third row. Uh, yeah, sorry, replace the I will store the first row in the temporary variable, and I will make the first row similar to same as the third row, and then I will replace the third row with the first row, that is the temporary. Okay, if I run this command, so my first row, so this was my original augmented matrix. Now my first row is swapped with the third row. Okay, so now if I see the first column, so this is the biggest element, then rest of the two elements are smaller than this. Fine. Now I will go to the second and third row. So since we have we have checked the first column, then while moving to the second column, we will be only checking these lower part of this matrix. We need not check the whole matrix from the first part, right? Yeah. Uh, I think, fine. We can do the second row also. So we need to take everything from the second to the end of the second, fine, and rest I will just copy this. First I will run these two. So if I look at this matrix, then first if I look at call 2, okay, this is my call 2, and if I look at the maximum of this, then I need not change anything, right? Because this is already the maximum. This is already sorted based on that order. These two elements are same, right? So I just need to do, and afterwards I will, if I go to the third operation, then I just need to check the third element, right? So there is nothing below that, so I need not to do anything. So I just need to change these two, the first and the second row, or the first and the last row for this pivoting operation. Okay, and this is what we are getting from this also. So if I just run this part, I will just remove this. And this, I run just this part. So this is what we are also getting. Okay, this is what we were getting based on hard coded, right? This is just automating that part. Rest of the command is similar to the Gauss elimination. We are doing the making the upper triangular matrix and then back substitution. So any doubt to anyone why we are doing this pivoting, and what do we do using this loop? What are we doing using this loop? And so if there are no questions, then let us go to the next part, which is the Jacobi iterations. So in the recorded lectures, we have seen two methods. The one is Jacobi iterations, and the other one is Gauss-Seidel iterations. So both of these methods are similar, except in how we are doing the updating part, how we are updating the latest x values. What is happening in Jacobi iteration is is we are always using the old value of x for calculating the new value of x, right? So what is happening over here is, suppose I have a problem x is equal to b, right? uh, what this statement means is, suppose I have some x new, uh, some x old, and I have some x new. Okay, I will, if I will just do the matrix multiplication, this matrix multiplication, then for the first, okay, let us try to do it using a simple 2 cross 2 matrix example, right? Let us use this. Okay, that this will become clear then, right? So let us create the A matrix, A comma 1, 1 comma 4. B matrix is 1 comma 1. Yeah, so the problem to this solution is 1 comma 1, that we all know, right? It's a simple problem. Now what I'm trying to do is, I'm trying to do a guess. I will just take 1.25, 0.25. Okay, then I can do this matrix multiplication, right? So 4 times x1 plus x2 is equal to 1. And now if I do the first part of that, and do this, let me create a slide. Comma 4, 1 comma 4, right? Similarly, by the matrix is 1 comma 1. Now if I try to write x1, then my x1 would be a 1, b1 minus a 1 comma 2 multiplied by x2 divided by a 1 comma 1, right? Similarly, my x2 would be, so I will use the first equation to calculate x1 and the second equation to calculate x2. Fine. Uh, this would be, so copy this, b2 2 comma 1 x1 2 comma 2. Fine. So now what happens in Jacobi is, I take some initial guess. So I'll take some initial guess 1.25 comma 0.25, and then I use this same initial guess for updating this x1 and x2. So this x1 is basically old value of x2, and this is my old value of x1. This is my new value of x1, new value of x2. right? So in this case, what will happen is that my x1 would be b1 minus a 1 comma 1 comma 2 multiplied by x whole 2, okay, divided by, so yeah, bracket is closed, a 1 comma 1. Similarly, I will write x2, that would be b2 minus a 2 comma 1 multiplied by x whole 1 divided by a 2 comma 3. Let me put all of this in a straight line. You can easily run this again. This will become 2, this will become 2, this will become 1, 1, 2, 2, 2, right? And we will replace the x old with x after every iteration, right? This is basically the update rule is we are using the x old to calculate the new x, and then we are replacing the x with we are replacing the x old with the new x, right? So right now our x old is 1.25 comma 1.25. I run this, my x old becomes minus 0.625 minus 0.625. Run this again, becomes 2.656 2.656. Mention this. I run this again 1. So I continue to run this. So now my solution has converged, right? So it has converged to yeah, it has converged to 0.2 and 0.2. Okay. Yeah. So here in this problem, the B matrix was 5 comma 5. That is why the answer is 1.1. So I made my B matrix 1. So my answer would be 0.2, 0.2. I change my B matrix to 5 comma 5 only, and I run my x old. I run this entire thing again. So my x old becomes 9.365. Same thing again, 1.0156, 0.99, 0.01, 0.99, 0.01. Yeah. So you see, it has converged to 1. After how many iterations? I think it got converged to 1 in about 8 iterations, 7 or 8 iterations, right? Let us. So this is Jacobi iteration. Okay, we are using the old we are using the old x value only for calculating the newer x values. The difference between Jacobi iteration and Gauss-Seidel is that in Gauss-Seidel iterations, we use the new value of x as soon as it's become available. right? So as soon as we get the next new x value, we use that x value in for the later part of the calculations. Like in this case, I had made that. Where did I? Yeah, like in this case, after the first iteration, when I got my new value of x1, so for the second calculation for x2, I will use the new value of x1. So this is for Jacobi, right? And this is for Jacobi. I think it's still visible, right? And this is for Gauss Seidel. So as for the first one, we will be using for first update of x1, we will be using the old value of x2 only. But now for the update of x2, since we have got the new x1, we will be using the new x1 over here. Similarly, if we had other more number of variables, so we'll be using the newer values for them also. That is what is written over here. So as soon as the new value of x becomes available, we will be using that. So this is a 2 cross 2 problem, right? So for the first one, for the first one, we are using the newer value. For the second one, for the first one, we are using the old value, and for the second one, we are using a newer value. If it would have been a 3 cross 3 problem, then like suppose I am talking about the ith one, right? Uh, Suppose I am talking for the ith problem, right? So j is equal to I. So for I minus one number of these x values, I will be using the newer ones because I am starting from the beginning, right? So if I write over here, yeah. So like if I have a 4 cross 4 matrix, right? So for the update of the first one, how do I mark? Okay, I think I cannot. So if I copy this matrix, let me try to copy this, make a new slide. Yeah, okay. So this one will be multiplied by x1, like not x1. So we have x2, x3, x4, right? So then I have some random value. Mm, right. So I take this and this is equal to. So for Jacobi, we will be using the old value only, but for Gauss Seidel, uh, for this, so this will be multiplied with x1, x2, x3, x4. So for x1, I will be taking 0.5 minus all the variables for x2, x3, and x3, right? And I will get a new x1. But while I am calculating for x2, I will be using the older values of x3 and x4, but the new value of x1. Similarly, when I am calculating for x3, I will be using the older values of x4, but the new value of x2, x1 and x2. So if I consider this as my I, this is my current I look at, let me write j. So if this is my jth number of jth variable, then I will be using newer values of j minus one number of variables and old values of j plus one to whatever the end variable is, right? So I will be from 1 to j plus 1, I will be using the newer values, and for whatever value variables from j plus 1 to n, I will be using the older values. Fine. So why this helps is that we are using the latest value of the variables. The convergence becomes a much faster than compared to Jacobi. Also, this is like a little bit more robust than Jacobi. Any doubt in this? Fine. So I will just show an example related to this. Gauss cycle Jacobi. Yeah. First, we will look at Jacobi, the simpler problem. So this is a general purpose code. I had written it long back. Yeah. So this is a general purpose code. We just need to change the A and B matrices, and the code will run fine. Uh, I am currently using this problem only, the example problem. So I am giving some tolerances values. So uh, right. So here, like we have this stopping criteria, right? If the total sum of all the older x variables and the newer x variables, so we take the norm of the error, like the difference between the new x and the old x, and that should be less than some threshold value, some tolerance value. Then we uh, stop the stop the iterations, right? And another check that we need to make is that we also need to check that our overall the problem is ax minus b, that is the linear problem, is also less than some tolerances. Sometimes what happens is that these values do not change. Like there is very little change between the two iterations, old and new. So this tolerance is satisfied, but this tolerance is not satisfied. The overall problem is still not close to zero. So that is so we need to check both of these two conditions, right? So this basically ax minus b, a norm of x minus b, this basically is the residue of the problem. So we need to also make sure that residue goes to zero, and this is the change in the x values, right? So we need to check these both of these two. In this, I'm only checking one of them, but I can add one more. Okay, let me just add that also. So relative error and uh, residue tolerance. I will add one more over here only. Mm, residue error. I just want to initialize these were two values to some large numbers, right? So I'll just initialize these two. These are the initial values of error, right? And these two are the tolerances. So relative error, residual error for tolerances, and relative just consistency in variables. Hmm. So I will make this rel tall, and I will make this res tall, and this should be the error, right? So I'm calculating the relative error over here. I just need to calculate the absolute error also. And sorry, residual error also. So residual error. This is the I am doing this after this loop has run. So I will just use the x new minus my v vector. Okay. So the absolute of this should be until this is greater than this tolerance, this while loop will continue to run. Okay, so I will just now go through this program. So this is the initialization of the tolerances and the current error values. This is for the number of iterations. So these are my a and b matrices. I am initializing my x hold, so some random. Okay, so for now make this compatible to size of b. So this is I'm initializing my initial conditions to some random values and my x new to zeros. Okay, so this is just initialization. Anyways, this is not important, right? This x hold initialization is important. So I will run a while loop. So while my relative error is greater than my tolerances and my residual error is greater than my residual tolerances, this loop will run. What I am doing is for the size of a comma l. So this will give me the number of unknowns or the number of rows in the uh, in the in the sorry number of columns in the problem, right? So in this case that is 2. So this will run 2 number of times. Okay. Uh, what I am doing, I am storing my x old in a some temporary variable, and I am making all the elements up to that. I am making that specific element 0, right? So suppose in this case, for this case, if I'm running it for the first for x1, then I'm making I'm storing. Okay, I will use a breakpoint method to explain this properly. Run this. So right now my x old is 0.5285 and 0.1615, and my x new is 00, right? So my I is 1, my x temp is same. I am just making now the first variable of x, the first element of x temp 0. So now my x temp has is become 0 and 1.615. Why I'm doing this is like I am using here the entire first row, okay, and multiplying it by x temp. So I don't want the first element to be used in this multiplication because we are calculating for that element only. We are updating that element only. So I'm making that element in the temp variable 0. So when I do this multiplication, that element will not be included. Okay. So if I just take this, right. So this is 4 comma 1. This 4 comma 1, and my x temp is 0 1.6, 0.1656. So when I do this multiplication, this first element would not be used, right? And I will be just using the b1 minus uh, a 1 comma 2 multiplied by x2 and divide by a11. Okay, and then so this is for the x1. Now for x2, right? So this time I'm making my second variable. This time I'm making my second element of x times 0, because I will be multiplying the first element. I will be multiplying the first element only, right? Yeah. So this runs. So this entire loop ran once. Now I calculate my relative error and my residual error. So my relative error 1e minus 4 and my residual error is also 1e minus 4. Okay. And I am storing my newly calculated x into the old variable, so that when I rerun the loop, I will be using this new values of x. And I just making the okay. So what is the issue? Operands to the logical and or operators must be convertible to logical scalar values. Okay. Why is this not convertible? Okay. Uh, should work. What else can I do? Just do multiplication over here. That should work. Yeah. So instead of and, I'm just doing multiplication. So when both of these conditions are true, then only this whole multiplication would become 1. Otherwise, it will be 0 if any of this condition is not satisfied. Fine. So now, yeah. So what I gave 1e minus 4. So you can see after one iteration. Let me put a while before here. We'll run this again. Step. Yeah. So my relative error right now is 0.5131, and my residual error is, yeah, that was the issue. So I needed to take a norm over here. Now I think this should work. So my residual error was a 2 cross 1 vector, and my error residual tolerance was a single variable, single element. My residual error is 1.4933. So after one iteration, these are my current errors, and these two set conditions are not as satisfied, so the loop will run again. Okay, so I will just continue. Yeah, so you can see right now my relative error is less than my tolerance, and my residual error is also less than my tolerance. Okay, so now the loop will exit. I think I ran the problem again. Sorry. Yeah. So after nine iterations, we can see that the problem converges. Okay. If I go to the Gauss seidel for the same problem statement, what is just changing? I need to change with Jacobi is uh, I was making this extemp. I was storing this extemp xold into this extemp, and then I was multiplying this extemp. Okay. I need not to do that because whatever extemp I'm getting, I'm using that only. Okay. So I initialize my extemp to some initial condition, randomly some initial condition. I'm storing my xhold to that xint. Okay. And then what is happening over here is I'm just making the first element zero because what I was doing over here, I don't want to multiply this with the element that we are calculating it for. So I make that element zero over here, and then I do this multiplication. So this extemp updates after every iteration. Here what was happening is that we were storing this x old in extemp, and then we were calculating x new. So we were not using the latest value of the uh, up to I minus one element. We were using only the old values. In this case, we are not using any old values. This extemp is updated, and for the next iteration, we are using the same extemp, right? So if I run this, how do I do this? Okay, let me just output the extemp values after every iteration so that we can see. Sorry, next will be yeah, I'm initializing it randomly. So So yeah, you can see iteration 6. So this problem ran only in 6 iterations as compared to Jacobi where it was running in 4 number of iterations. So if I just okay, I wanted to show you I have this code side by side. Yes. So in this case, I am making the current element of extemp 0, and then I am doing these operations and I am storing it in extemp temporary extemp only. In Jacobi, what I am doing is I am storing the x old in extemp. I am making the current variable of extemp 0, and then I am doing these calculations and I am storing it in x new. So for next iteration, the older values of x have not changed. It's still the x old value. But in this case, since I'm using the same extemp for calculations and same extemp for updating, so I am for every iteration I'm using the new value of extemp, right? And so we can see, I will add this tolerance also, same for the codes. Program structure is similar for both the codes, just there is a difference in the update rule. So this is correct. I will need to add this line of code. Fine. I will stop the display and I will just display the number of iterations. Fine. Okay. So this ran for in 6 number of iterations for the same problem, and Jacobi ran in 9 number of iterations for the same problem. Fine. So we can see that when we are updating it at the same time, then Gauss Seidel is faster as compared to Jacobi. Okay. Now we will look at this problem, the problem that we are doing, that we have been doing until now, the 3x3 problem. Yeah. So let us look at this problem using Gauss Seidel and Jacobi iterations. Okay. So I will just comment out this part, and I will comment out this part. Okay. So same problem. We will you can see this matrix, it's not diagonally dominant, right? So we will just do these row operations to make this diagonal, not entirely diagonally dominant, but some sort of dominance will be there because we are replacing. So if I will just run this part. Okay. This is my current A, and I replace those two. So this is my new A. So I've replaced the third row with the second row and second row with the first row to the third place. So there is some sort of diagonal dominance in this matrix, because we can see that this is another diagonally dominant part, not diagonally dominant, but after pivoting in this column, this is the largest part. So all the values below this is 0. In this one, even though uh, 3 is greater than 2, but compared to this where we were dividing 2 by 1 and then 3 by 1, in here we are dividing 1 by 2 and 3 by 2, so some sort of uh, dominance is still there, right? And we need, the last row is not that significant, so last column is not that significant, so we leave it as it is. Not as it is, but we don't bother with that. Now I'm doing the same, these iterations, the Gauss Seidel iterations on this problem, and we will see. So it ran in for 22 number of iterations. Finally, what I'm getting is, okay, let me display that also. Mm, time. So it ran for 22 number of iterations and we are getting this. So 1, 2, 1. This is the same as what we were getting earlier, right? So if I run a backslash d, so this is similar to what we are getting. If we make our tolerances much tighter, instead of this, if I make this -6, then we will get better iterations, but the number of better solution, but the number of iterations also increase from 22 to 32. Okay. Now I will do the similar thing with Jacobi. We'll see how this goes. Okay, fine. Comment this out.
Not yet. Not yet. What? Yet. I think she has
Yeah. So it ran for 2025 iterations and still I'm not getting my correct answer. See,
so many of them.
my final solution is still like some rubbish values, infinity, infinity, 0. So the same problem, same structure, Gauss ideal works. I'm getting a proper solution, but Jacobi does not work. Now, why is that happening is because this matrix is not diagonally dominant. Still for we have after pivoting we get some sort of dominance, but it's not completely dominant. So for such problems Gauss ideal works. I'm not sure if this will work for every problem or not, but for this problem it works. But Gauss ideal but Jacobi does not work. Okay. So it ran for some 2000 iterations and still I'm not getting a correct value. But if I change this matrix to some diagonally dominant matrix, so yeah, if you see this, so this is a diagonally dominant matrix. This is true, not strictly diagonally dominant, but still it's diagonally dominant. In this, the largest element is 4, so greater than sum of those two, and in the last row also, 4 is greater than sum of these two. But for the first row, there is equality. There is no strict inequality. So it's not completely diagonally dominant, but yeah, it's diagonally dominant. It's not strictly diagonally dominant. So for this problem, first let me do the backslash operator. Yeah. So this is the solution for this problem. And if I do a Gauss Jacobi on this, sorry, if I run a Gauss Jacobi on this, yeah, so after 57 iterations, rank of A is 3. Also 3. It should converge. It's converging, but it's not converging to the correct answer. Why is that happening? Okay, sorry. Yeah, I was outputting the wrong, displaying the wrong variable. Okay, so Jacobi, it runs for 59 iterations and I get this value, which is similar to what the final solution is, 0.667, 1.667. Okay. Yeah. So Jacobi iterations work perfectly fine for diagonally dominant matrices. If the matrix is not diagonally dominant, So the Jacobi will not perform nicely. The Gauss Seidel, it may work or it may not work. Okay. Uh, Fine. And we also saw that Gauss Seidel is a little bit faster than compared to Jacobi because we are updating the x values as soon as we get it. Now coming to the last part. So TDM algorithm, right? So we will try to solve this problem. So it's a second order differential equation. We don't have any other condition, just a second order differential equation. We have two boundary conditions. So at zero, we have temperature TH, which is equal to 1. And at x is equal to 1, we have TC, which is equal to 0. So we first discretize this using central difference method. So we discretize it in uh, n number of elements. So if I take these two elements, if I take the first element, second element, and third element, and I am discretizing this distance as delta x. Okay, so my delta x is 1 upon n plus 1, n minus 1. So n is the total number of elements I'm discretizing this into. And if I write the central difference formula for this, then I will be getting something like T3 minus 2 times of T2 plus T1. T1, and I just divide this by delta x, right? So this will be my yeah. So this will be my delta x square, and this will be my d square t by if I make it on a pen, then I think it should be better. But okay, dx square, and there, fine. So now I do this for all the elements across the width of this, right? So I will get if I do all the so for the boundaries I have a 0, and for the first one, right? So this is equal to 0. So and I think there should be a half over here because we are differentiating it twice. So 2 times delta x and then another delta x. So it should be 4. This it should be 4. 4 delta x square. But since we have a 0 over here, so all of this goes to that goes there, and we only get this part out of it equation, right? T3 minus 2t1 plus t minus 2t1 plus t1. Okay, and we can generalize it to get a equation which is similar to this, right? So we get ti I plus 1 minus 2ti plus ti minus 1 is equal to 0. So this is our discretization, and now we just simply uh, convert this into matrix notation. Okay, so for the first element for this element we have th is equal to 1, and okay, so there would be no ti minus 1 and ti plus 1. Okay, so we will get a ti plus 1, but there would be no ti minus 1, right? uh, so I will get the equation which will be t2 minus 2t1 is equal to 0, right? From here I will get t1 is equal to uh, t2 by 2. So but I already know my t1 is 1, so I get my t2 as 2. Okay. uh, Similarly, if I write it for the second part, for the second element, so I will get something like t3 minus 2 t2 plus t1. Okay, I don't know why it goes, it makes a line. It's very irritating. So we get t3 minus 2 t2 plus t1 is equal to 0, right? So if I look at this part of this matrix, so I will get my 1 over here, minus 2 over here, then another 1 over here, and this is a 0. So it will become 0 over here, right? Similarly, for the third element, so I will get something like t4 minus 2 times of t3 plus t2 equal to 0. So I will get a 0 over here. There is no element for t1. For t2, I will be getting a 1, then minus 2, then 1, and then all zeros again, right? Similarly, I will get a structure. So it's a tridiagonal matrix. That is that we will be getting 1 minus 2 1, 1 minus 2 1 0 0 0, 1 minus 1 0 0. And okay, so and this will be like the vector of unknowns t1 t2 t3 up to tn, and then we will have the constants over here, b vector over here. So we know that t0 is 1, so we will just write 1 over here. The rest of them would be 0, because uh, like from this equation we are getting a 0 over here, so the rest of them would be 0, and the last of this one would be like this is just a 1 over here, right? If I write it for the last element, so I would get this would not be there. I can simply write it. I need not to use this discretized equation, because I know the boundary conditions beforehand. So I can simply just write 1 1 over here and t1 tn. So this all of this would be 0. So it will be multiplied by tn only, and that is 0. Okay. So I just need to create this part of this matrix, the inner part of this matrix, right? The first row I know it will be 1, and this 0, and this will be 0, and last one. Okay. And now I just need to take inverse of this matrix to get the value of unknowns. Okay. So if I go to MATLAB, I think I have, yeah, so we can simply use Gauss Seidel itself. So if we do that discretization, we will get a matrix which is something which is like this. So if it's a 5 cross 5 matrix, so we have we have 4 number of elements and 5 nodes. Okay, size of A. So it's a 5 cross 5 matrix. We have 4 number of elements and 5 nodes, T1, T2, T3, T4, T5. And we know that at the end value we have the at node 0 we have boundary condition 1. At node last node, fifth node, we have boundary condition 0. So if I uh, check determinant of this A matrix, It's uh, yeah. So determinant is 4. Is determinant and this. I get a final solution is this. Yeah, so determinant of A is 4. So yeah, non-zero value. So I get rank of A, it's 5. And if I look at rank of augmented matrix, so I get 5. That means a unique solution exists to this problem. Okay. And if I run this Gauss Seidel program, then I get these value of the nodes. Right. Now we can check with the analytical solution. So the analytical solution for this and the given boundary condition is 1 minus x, right? So whatever the node is, like for the first node, we should be getting a value of 1, and for the last node, uh, if we take L as 1, okay, then for the last node, we will be getting a 0. And so it's a linear, like it's a, if I plot this, yeah, so I get a line with a negative slope of 1, okay. I I need to make this like this is 1. This is not 5. So yeah, and this is the numerical solution that we are getting. If I plot the analytical solution on the same plot, and so my analytical solution is 1 minus this value, right? So both of these plots superimpose on one another. It need not be true for other problems, but since for this problem it is happening, right? So with this, okay, so yeah, I end this session. So I think we don't have time now. So this is what I wanted to discuss today. If you guys have any questions, then you can ask. Otherwise, we can end this meeting. No questions? Then I think we can end this meeting. I will share the slides and the codes on the Google Drive link. You guys can check this out. Okay. Thank you.